In 1931, Linus Pauling developed the orbital hybridization theory to explain the structures of simple molecules. For instance, in methane, a carbon atom forms 4 bonds by using its 2s and 3 2p orbitals. It might be inferred that the carbon atom would form 3 identical bonds at right angles using the p orbitals and a 4th different bond using the s orbital in some arbitrary direction. However, methane has 4 equivalent carbon-hydrogen bonds. The bond lengths are equal. The angles between the bonds are equal as well. Pauling supposed that in the presence of 4 hydrogen atoms, the s and p orbitals form 4 equivalent combinations which he called hybrid orbitals. Hybrid orbitals are assumed to be mixtures of atomic orbitals, superimposed on each other in various proportions, which are suitable for the overlapping with orbitals of other atoms to form chemical bonds. In light atoms, such as carbon, nitrogen, and oxygen, the atomic orbitals used are the 2s and 2p orbitals. In the case of sp3 hybridization, the s orbital is mixed with all 3 p orbitals. All 4 sp3 orbitals are equivalent and cylindrically symmetric. Their symmetry axes have tetrahedral arrangement with around 109 degrees 28 minutes angles between each other. A sp3 hybrid orbital can overlap with one orbital from another atom to form a sigma bond. For example, in ethane, both carbon atoms have sp3 hybrid orbitals and bond to 4 other atoms. The carbon-hydrogen bond is the overlap of the sp3 hybrid orbital of a carbon atom and the 1s orbital of a hydrogen atom. The carbon-carbon bond is the overlap of 2 sp3 hybrid orbitals. It is a single bond. All the bonds in ethane are sigma bonds. In the case of sp2 hybridization, the s orbital is mixed with 2 of the 3 available p orbitals, usually denoted px and py. The third p orbital, pz, remains unhybridized. All 3 sp2 orbitals are equivalent and cylindrically symmetric. Their symmetry axes lie in a plane with 120 degrees angles between each other. A sp2 hybrid orbital can overlap with one orbital from another atom to form a sigma bond. For example, in ethylene, both carbon atoms bond to 3 other atoms and have sp2 hybrid orbitals. The carbon-hydrogen bond is the overlap of the sp2 hybrid orbital of a carbon atom and the 1s orbital of a hydrogen atom. All the carbon-hydrogen bonds in ethylene are sigma bonds. Between the carbon atoms, the overlap of 2 sp2 hybrid orbitals form a sigma bond. The overlap of the remaining p orbitals form a pi bond. So, the carbon-carbon bond in ethylene is a double bond. All the atoms in ethylene are coplanar. In the case of sp hybridization, the s orbital is mixed with one of the 3 p orbitals, usually denoted pz, resulting in 2 equivalent sp orbitals and 2 remaining p orbitals, px and py. The sp orbitals are cylindrically symmetric with respect to the z-axis. They have an angle of 180 degrees between each other. A sp hybrid orbital can overlap with one orbital from another atom to form a sigma bond. For example, in acetylene, both carbon atoms bond to 2 other atoms and have sp hybrid orbitals. The carbon-hydrogen bond is the overlap of the sp hybrid orbital of a carbon atom and the 1s orbital of a hydrogen atom. Both the carbon-hydrogen bonds in acetylene are sigma bonds. Between the carbon atoms, the overlap of 2 sp hybrid orbitals form a sigma bond. The overlap of the remaining px orbitals form a pi bond. The overlap of the remaining py orbitals form another pi bond. So, the carbon-carbon bond in ethylene is a triple bond. All the atoms in ethylene are collinear. Not all electrons in hybrid orbitals are shared by atoms. A lone pair refers to a pair of valence electrons that are not shared with another atom. A single lone pair can be found with atoms in the nitrogen group. In ammonia, the nitrogen atom has sp3 hybrid orbitals and forms 3 sigma bonds and 1 lone pair. In pyridine, the nitrogen atom has sp2 hybrid orbitals and forms 2 sigma bonds, a pi bond and 1 lone pair. In hydrogen cyanide, the nitrogen atom has sp hybrid orbitals and forms 1 sigma bond, 2 pi bond and 1 lone pair. 2 lone pairs can be found with atoms in the chalcogen group. In water, the oxygen atom has sp3 hybrid orbitals and forms 2 sigma bonds and 2 lone pairs. In formaldehyde, the oxygen atom has sp2 hybrid orbitals and forms 1 sigma bond, 1 pi bond and 2 lone pairs. The halogens can carry 3 lone pairs. In hydrogen fluoride, the fluorine atom has sp3 hybrid orbitals and forms 1 sigma bond and 3 lone pairs.